Hello, hello, hello.
Good morning.
Good morning. Good morning. Good morning. Quick. All right, hold on one second. Good to see you. Good morning. Okay. Good morning, Nasreen. Good morning, Colin. Good morning, Brandon. Good morning, Charlene. Good morning, Brittany. Oh, I gotta wait. Oh, that should be a portal, a wave. All right, I'll try to remember or remind me. Brittany. Good morning, Xavier. Good morning. Also, if I ever can do this in rhyme or rhythm, I should get a portal. Okay, and good morning, Ariana. Good morning, Alexis. Good morning, Maria, and the chat. Hold on. Good morning, Gaia. Good morning, Nasreen for the double. Good morning, Adenelsi. Someone else is here. Good morning, Brittany. Good morning, Chanel. Good morning, Alexis for the double. For the double. Good morning, Mickey. Good morning, Ariana. And there, someone just came in. No, that. Oh no. Okay. Okay. Let's get rolling. I'm still catching up with you guys. If you haven't gotten all your work back yet, not you, it's me, and I'm aware of that, and it's coming. Who else? Oh, good morning. Did I say Mickey? Good morning, Ariana. Good morning, Ryan. Um, so let's just get rolling. Yes. Okay. When it is indeed you. Huh. Wow. Right. Yes. All right. Agreed. Um, right. Um, when I say let's get rolling, what I mean is let's officially enter the land of two dimensions, which Zoom is perfect for. And I mean that like big old duck, it, big old duck and lab 3 and lab 4 are all meant to transition us from one-dimensional kinematics to two-dimensional kinematics. So we've been sort of in we've been softly in two dimensions for a little while now, but let's make the transition official. Okay. We're officially entering two-dimensional kinematics. Again, technically, especially if you were like doing web searches for help or things like or looking in textbooks or whatever, officially everything we just did was known as one-dimensional kinematics or the constant acceleration equations. I mean, if you're thinking of things in terms of everything we just did was the constant acceleration equations, and that was ultimately, the topic was ultimately constant acceleration. But all of that fell, or the last topic, let's say, but all of that fell under the larger rubric of one-dimensional kinematics. Now, kinematics means motion, but everything in physics is about motion. Like truly, everything in physics is about motion. So, what is kinematics specifically? What it really means is defining the terms of motion. Everything we've done so far really has been that, but we like a lot of triple equal signs because really what we're doing thus far is defining things like velocity, average velocity, instantaneous velocity, constant velocity, and then acceleration, instantaneous acceleration, average acceleration, constant acceleration. Um, and even all the equations we've got in a way, and this is why in a way everything we've been doing is very mathematical in the sense that once you just think of these ideas and the words that express them and then the symbols that express those words, you turn the crank or we turn the crank and we realize a bunch of things about the world. In other words, a lot of what we're discovering about the world thus far, we only needed our minds to discover. We didn't even really need that much sensory data to confirm. So kinematics means the definitions for motion. Now we want to move, but everything we defined or every equation, this is like the important thing I'm trying to say. Every equation that we've gotten so far strictly speaking, applies to motion in a line. That's why the first homework assignment was called number line, because really everything we've been analyzing is along a axis where you have 1 degree of freedom. You can either go forward or backward, or east or west, or north or whatever you want to call, or up or down, whatever you want to, which you ultimately mathematically designate positive or negative, right? But that's the whole world until big old duck or lab 3 or lab 4. So when I say now that we're going to enter 2 dimensions, I'm going to say two. Number one, I actually mean we're going to enter the land of any number of dimensions that's higher than one. I mean, technically, really, you could write in your notes. What we're really doing now is figure out how to apply one-dimensional concepts to n number of dimensions. That's really what's happening now. Um, uh, yeah, that's really what's happening now. And then number two, I mean, I kind of just said this, but we're not going to get the reason you were even able to do big old duck or lab 3 or lab 4, like without some grand official introduction like I'm giving now, is because, as you may have noticed, there aren't actually new equations, or even there are not new equations or new discoveries once we go from an x-axis to an x-axis and a y-axis, or even x, y, and z. There aren't new discoveries, there aren't new equations. What there is a method for taking what we know about the line and applying it or extending it to the plane. And that method is this. Surprise, surprise. So about obviously I'm going to go to the next page in a second. Just surprise, surprise. I'm going to tell you something that in a way you already know, in a way you were already sort of taking for granted when you did the big old duck, or you did lab 3, or you did lab 4, like but like so much in physics, like you knew it, but you don't necessarily know that you know it, or know that it's like a thing that you're knowing. And more to the point, one might not know how directly productive and important it turns out to be. And what it is, that I'm about to write on the next board, what it is another form, another way of saying Galileo's principle of relativity. Okay. And again, my sort of argument, or my like research stance, or whatever, like my perspective on the world, is that like everything we do in physics is another interpretation or implication of the fundamental idea that we could believe that we're standing on a rock that is moving 665,000 miles an hour past the sun, and yet we could like not feel that or sense that at all. Like, I'm serious. Like that idea. What is that idea really? That idea that the laws of physics are the same in all unaccelerated reference frames, coordinate systems. The laws of physics are the same in all unaccelerated coordinate systems. That's why we could be on the Earth and not feel that it's moving, right? Or whatever. That's why you could get into an elevator and not throw up. I mean, not to be, but right, you know what I'm saying? Or you could be in an airplane and like be preoccupied with the movie rather than the fact that you're, going 600 miles per hour. Um, that whole idea that velocity is a relation between two objects, not a property of one object. That idea is the hub of physics. I'm going to argue that, like, I don't care what physics class we take, it's at the heart of everything we do. And we just keep turning the crank and seeing more implications of it. So here's the fourth implication, the fourth form of that idea. And it's how we extend our knowledge from one dimension to higher dimensions. The idea is this: Well, I'm gonna say a couple. I'm gonna write it. I promise. I'm getting to. But the idea is, if the laws of physics are the same in all coordinate systems, if we really take that all unaccelerated coordinate systems, if we really take that seriously, then we pause for a second and say to ourselves, "What's the simplest possible coordinate system I can imagine?" The simplest possible rhetorical question. The simplest possible coordinate system I can imagine would be a coordinate system with one axis in it, right? Like not even a graph, not even a piece of graph paper, but just like a number line is the simplest possible coordinate system I can imagine. If the laws of physics are the same in all unaccelerated coordinate systems, then the laws of physics have to be the same whether you're looking at the x-axis or the y-axis or the z-axis. In fact, whether you call it x or y or z is totally in your head or my head, right? Like there is no objective x-axis in space. There's no objective y-axis, right? Just like there's no objective 30 miles per hour in space. It's all comparisons. Same thing, X, Y, Z are all comparisons. Whatever's true in a axis is true in another axis. Therefore, here I go finally. Therefore, form number 4 of Galileo's principle of relativity is okay. This is the principle, or this is the form of the principle. I'm going to read it out loud. I'm also going to change the view screen. Wait, and by the sorry, there's something we are recording, right? As far as you can tell, like, can anybody do you have indication on your side that we're recording? Because my thing is not indicate. Does any or did it tell you when you logged in? Does it? Oh wait, but yes. Okay, thank you, Maria. Oh, and Colin's it says it is. Okay, great. Because I don't know why the button isn't. I do, and it is recording. Okay, great, great. Thank you. Um. So wait, back up for a second because I missed also that Colin asked a really good, totally fair, really good question in the chat. Oh, he just asked it. Okay. So the truth of the matter is that's a real so he's saying Colin's asking like, wait, but like, isn't the Earth actually accelerating? And yeah. So strictly, and we're gonna get to that too. Strictly speaking, because the Earth is continually changing its direction, that does count as an acceleration, yes. And that's not a technical point. I mean, it is important that everybody in this class do understand, especially now that we're moving into 2 dimensions or 3 dimensions. Acceleration means change in velocity. Velocity is speed and direction. So indeed, if you either change your speed or you change your direction or both, then then you are in fact accelerating. So every time I talk about the Earth, you are right. I mean, Colin is right, and it is right to consider. I'm oversimplifying whenever I talk about the Earth as an inertial frame of reference. When I talk about the Earth as like something that you can't feel any of its motion, in fact, I am oversimplifying. In truth told, the Earth actually, because it's constantly turning, uh, continually turning, it is technically accelerating, and ultimately there is evidence of that. Ultimately, things do happen on Earth. Ultimately, that would not happen if it weren't accelerated. There's things. Well, I'll name a couple examples in a second. So that's completely fair, completely true, and completely thoughtful. The reality is, when it comes to the acceleration of the Earth, it's what most people, or a lot of people tacitly think about the velocity. The acceleration is so small because the Earth is carving out such a huge ellipse. Like it is curving it through space, but so gently, so smoothly. Like yeah, just that. Like it's not a tight circle. It's not tight. It's a really gentle, progressive curve that the Earth makes, that the acceleration in magnitude is so small that in most normal or daily typical circumstances, we don't notice it in the way that people tend to think is the issue with velocity. But velocity, that's not the issue. The velocity is so high at 65,000 miles an hour. There's no way we wouldn't notice it except for this interesting character of velocity. Now, the Earth is actually accelerating. I mean, I know there's a slight tangent, but just is such a fair question. There's no way not to honor it. The Earth is slightly accelerating, and that's why there are things known as, you may have heard of, like the Coriolis effect, which some people think of as like the toilet flushing thing. That's like a little bit mythical. But what is true, for example, is if you dropped a penny from the top of the Empire State Building, besides that, it like really would hurt whoever it would hit and all that kind of stuff. The truth of the matter is the Earth's acceleration and rotational acceleration is just significant enough that if you dropped a penny off the top of the Empire State Building, even without wind, or you dropped like a really dense like a super dense, super non-aerodynamic marble, I'll just, it is true that it will not land directly below your hands. Like even on a perfect day under like perfect conditions, it will land a little bit to the west, I always get it backwards, but it'll land at a slightly different longitude. Um, because ultimately we can't totally ignore the fact that not only is the Earth moving, but it's also rotating and revolving, therefore accelerating. So there are subtleties. I'm going to move on in a second, but Colin's absolutely right. I mean, yet there are subtleties. The magnitude of the acceleration is so small that mostly we get away with it in our daily lives. Um, okay, and in terms of the program of the class, like what are you supposed to do with what Colin just asked and what I just said or whatever? What you're supposed to do is like the larger principle is velocity is not a thing that is felt. Velocity is in the eye of the beholder. Acceleration is different. And that's why we care so much about acceleration. And we're going to develop that more in the next chapter, which is like F net equals MA. Like ultimately, we care about accelerations because they're associated with forces. Velocities are not. Okay. If you're thinking mathematically, what we're saying in this class, a big principle of physics is the first derivative of position with respect to time is a relation. But the second derivative of position with respect to time is a property. Like you actually can feel it. You feel when the airplane takes off or lands or turns or hits turbulence. You don't feel it like those are forces. And so Colin's right. Like even on planet Earth, there are subtle ways in which we do feel forces due to the Earth's rotation. But yeah, but they're subtle. Okay, I'm gonna keep going. No problem. Great question. Okay, wait. I'm gonna keep. Okay. So back to the program. Yeah. What this says right here is every n-dimensional experiment or problem of physics. In other words, everything in empirical reality or theoretical in the world or in your brain, it doesn't matter. Every n-dimensional experiment of physics is in fact n experiments occurring simultaneously yet independently. Okay, this is another one of those statements that sort of maybe, I mean, it might sound like gobbledygook, or if it doesn't sound like gobbledygook, it might sound so obvious as to not like be worth saying, but it's neither. What it's saying is like if the laws of physics apply to the x-axis and the laws of physics apply to the y-axis, then when something is occurring in both at the same time, such as Lab 4, or such as big old duck, if there's a phenomenon that is occurring in a plane or sorry, it says n, right, or cube, like a three-dimensional phenomenon, like you know whatever, like say the big old duck, you were actually shooting at an angle, not straight up, or or Lab 4, say you shot the thing off the table at an angle, not horizontally. It that wouldn't make it. You know what I'm saying? No matter how many dimensions you consider, the key insight of physics is that each one of those dimensions is its own little world of physics. So, what this really means on a practical level, what this really means on a practical level is that when something's well, what this says in English, what my handwriting says is on a practical problem solving level, each of our 1D equations applies one dimension at a time. Like we don't introduce new equations for the second dimension or the third dimension of reality. What we believe is that a plane is two dimensions that may involve things happening at the same time as each other, but each one is carrying out its own laws as though the other dimension did not exist. And that right, and that's the insight that I would not have necessarily known like until someone pointed it out to me. Like with the big old duck, for example, the whole point is this is happening like this is happening at the same time as this is happening. So you analyze this um, uh, physics, you analyze like the shot of Big Old Duck first, and you just do all your old equations, like y equals 1 FAT squared plus v naught t, whatever, as though nothing else is happening this way because you can, because the physics of this doesn't know anything about the physics of that. So you do the physics of this dimension to figure out how much time it would take the shot to get up to a certain height. And then you believe, correctly believe, that whatever that time is that you solve for applies to the x-axis as well, because they are occurring at the same time, simultaneously, as it says. But you then plug in that time to your equations on the x-axis, and you just run the same type of equations again, but with solving for a different variable. And the whole idea is that these equations didn't have to be altered at all just because of the presence of these equations. I'm going to say one last time, and then like I'm obviously going to start showing you in a different application, but and everything I'm saying applies to lab 4 as well, and definitely lab 3, which is really what I'm going to talk about in a second. The two key words to everything I'm saying right now, the two key words are simultaneously and independently. When a two-dimensional problem is really two one-dimensional problems that are occurring at the same time but are not affecting each other. That's the key, okay? So I'm gonna like get practical in a second, or we're gonna get practical in a second. But as well, so the practical thing is that what this ends up meaning in a lot of cases, well, the thing that Big Old Duck and Lab 4 had in common is that they embodied this concept so deeply that we believed you could do Big Old Duck. I mean, I'm not saying they're easy, by the way, they're hard, but one can solve Big Old Duck and Lab 4 without having explicitly like thought of the words behind this concept because I believe those two situations kind of naturally reveal the truth of this, whether you think of it in these words or not. And really, what I'm really trying to say specifically is what Big Old Duck and Lab 4 had in common is even though they both involve two dimensions, what they didn't involve is any angles. They did not involve any angles. So we didn't literally have to like embrace two-dimensionality in any explicit mathematical way. We could just think about verticality and horizontality. Now, ultimately, things in 2 dimensions can get a little bit more elaborate than that, and they sort of did weirdly in Lab 3. Um, like things can involve angles. And so then we got to be careful with this concept. And the upshot is going to be, I'm going to show you right now. The upshot is if we take this concept really seriously, that every 2 dimensional problem really is and happening at the same time, then what it really means is when things look complicated, when things are moving on diagonal lines, we break everything up into right triangles. Like we use all of our mathematical knowledge of right triangles because no matter what's happening, our principle is going to be we break it up into a horizontal piece and a vertical piece or whatever, an X piece and a Y piece. And we do, and then put all the knowledge back together at the end of the problem. And we do this from our mathematical knowledge of right triangles. That's why the front board here. It says GPR form number 4. That's what I'm teaching you as the concept in English. But then how it's going to manifest itself in math quantitative problem solving is that sorry, the meeting's being sorry. Is that anything you knew about right triangles from a math class specifically, you might want to write this down. I mean, I'm going to do it my own way in a minute, but the two key pieces of knowledge that you need from a math class to really deal with 2 dimensions, the two uh, mathematical pieces you need are Pythagorean theorem and SOHCAHTOA, right? Which I know everybody knows. Like, I mean, that's not usually what troubles people. As long as you know, but you need to know that you need to know it. Pythagorean theorem, like a squared plus b squared equals c squared. And SOHCAHTOA, like sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. As long as you know those two things, then that's what you need to know to do physics. And in my mind, and you can think about this later in your own way, in my mind, the statement that actually puts together SOHCAHTOA and the Pythagorean theorem is the statement that I have right here on the board. Sine squared theta plus cosine squared theta equals 1. You might think of that as an obscure trigonometric identity. Like hopefully you do, it's hopefully familiar. Like it is a trigonometric identity. But now that we're going to get ourselves reacquainted with right triangles with perpendicularity, bear in mind, in the back of your mind, track this. I think you'll see at some point, or like write it out, try to prove it to yourself. You'll see that sine squared plus cosine squared theta equals 1 really is just the Pythagorean theorem with SOHCAHTOA. It's SOHCAHTOA and Pythagorean theorem combined into one statement, which I find very elegant and fascinating. I'm not going to make a big, I mean, this isn't a math, I don't want to get, but I mean, if you just substitute in like opposite over adjacent squared plus that's not what I meant. Sorry, opposite over hypotenuse squared plus adjacent over hypotenuse squared um equals uh equals hypotenuse over hypotenuse squared. You'll see what I mean. I said that quickly, but just play around. You'll see what I mean. That is a way of saying Pythagorean theorem with the SOHCAHTOA tucked into it. Anyway, so that's the knowledge you need for us to start actually solving problems that involve angles. Okay, so here we go. So I'm going off script now, but hold on. I know where are we in the homework? I'm about to just like teach you give you an example that will help you with the future homeworks. I don't even know, and I know we have to talk about. I also we have to confirm the exam and all that. I know. So I'm going to set up this problem before it escapes my mind, and then we might pause for a second because I know there's logistical things we have to resolve. But hold on a second. But this example problem I'm going to give you right now is an example problem. It's not in a homework as such. Okay. Wait, I lost the screen. Hold on a second. Sorry. And I'm just looking at the oh, oh. Oh wow. Is that where we okay, actually someone just told me in the chat. Okay, hold on. Someone just said something very valuable in the chat. All right, I'm gonna here's fair enough because I'm a little bit behind, and I don't mean to make you guys feel behind. So we're gonna pause for a second. Okay, this is the problem that this is the example problem that we're gonna work on today. We still have 40 minutes. We're gonna sort of do it together. And yes, someone just reminded me that you do start getting into this stuff in homework 7. So yeah, this I'm transitioning to homework 7. But yes, if it's due, I will adjust the due date of that in a moment. I will go shift and look at where we are and shift things accordingly. I agree that we're like sort of starting the topics of homework 7 right now. So, well, I'll look at the due date in a second. I'm happy to, and I know anyway, and the exam stuff. But what I want you to do next, here's this problem. I'm going to ask you to think about it and try it right now in real time. I will go over it, before this class is over today, but I want you to first start trying it in real time right now. It'll also help you with homework 7 and all that kind of stuff. Um, um, the question is, if you walk 5 meters at 30 degrees northeast, so you walk 5 meters like at an angle, and then you walk 80 meters at 60 degrees northwest. So this is kind of like lab 3, right? Like you're going to do a thing that you could symbolize by an arrow. Then you're going to do another thing that you could symbolize by another arrow. And if you draw this if you draw this really carefully, even just by drawing it, you could, in principle, at least get a very good estimate for the answer. Um, so I recommend drawing an arrow that's like 8 units long and going off at a 60-degree angle, and then, sorry, a 60-degree angle, and then from the tip of that arrow, start the tail of a longer arrow, and oh no, yeah, the first one's like this, and then the second one's like this. Um, my question is, what is your total displacement and what that really means? Right? When you know what displacement means, it means final position minus initial position, taking into account direction, right? So the final answer that we'd be looking for in a case like this, we'd be looking at how far you walked in total, like your total distance, and in what direction did you walk in total, like it, meaning angle and points of the compass, just like I have here. I mean, we're now in 2 dimensions. So direction, it's no longer good enough to express total direction with just a plus or minus. Plus or minuses are still relevant to our lives, very relevant to our lives, but each plus or minus designation applies to one axis at a time. At the end of the day, where you're going in a plane is expressed by an acute angle and points of the compass. So this question is asking you, in effect, to picture an arrow and then another arrow put tip to tail with the first one. And it's asking you if you completed the triangle on paper or in your mind, if you completed the triangle with like a final big arrow that whose tail started at the original tail and whose tip landed on the final tip of these other 2 arrows. If you completed the triangle and drew one big arrow, how long would it be, and in what direction would it be pointing? Now, I'm going to shut up in a second and have you work on this honestly. And if you, well, maybe I'll even put you in breakout rooms. Actually, this is not a test or anything like that. I just want to whatever, get us all thinking. Um, um, it is totally an answerable question. I will tell you that if you kind of like lab 3, if you draw it really carefully, like if literally if you have a ruler or a protractor, or you're just like really good, it is true that whatever the third arrow, if you literally had a ruler that you used to make the other 2 arrows, and then you measured the third arrow with that ruler, and if you literally had a protractor, which I'm not really guessing that you do, but maybe you have an app on your phone, I don't know. Like I'm just trying to give you an idea that the more closely you draw the 2 original arrows to scale and put them tip to tail, then it is absolutely true that a picture will reveal the answer. So you could at least get a really good guesstimate of the final magnitude and the final direction that I'm looking for here. And that is what I'm looking for from all of you. I'm looking for a final distance and a final angle for what's technically called adding two displacement vectors. That's technically what you're doing if you draw this and guesstimate and all that. I will shut up in a second, but I also just want to make clear, like, so this is maybe it feels out of nowhere, maybe it doesn't. I don't know, but you could reduce this to a drawing thing, and your drawing would reveal at least something very close to the right answer. It would literally be the right answer if you literally drew it like on a computer or whatever, like that okay, it is an accurate set of concepts. However, I also want to tell you that what I'm going to show you after I let you work for a little bit and after I like deal with the logistics of your homework and stuff, that if you analytically, if you really take seriously form four of Galileo's principle of relativity, if you really take that seriously, and if you know how right triangles work, if you know how SOHCAHTOA works and Pythagorean theorem works, then you can totally get an answer to this and be the worst drawer in the world, as I am. Like there's an analytical way to get this answer that doesn't require a picture. And that's what I ultimately want to show you. I think you could figure it out if you think it through, but you may or may not. But all right, but that's okay. So wait, I'm just gonna ask you what I want you to do, what I want you to work on right now for a few minutes is this problem. First of all, please just raise your hand, electronic hand, if it's clear. Like you may not know clearly what to do, but is it clear what I'm asking? Like what I need you to work on right now? Just raise your electronic hand if you. Okay, awesome. Thank you. Awesome, awesome. Now I'm going to take quick vote too, and you can put your hands down. That's awesome. This is a weird question, but I might as well. I mean, would you like to be in? Put your hands down. Like, so thank you, Adam Elsie, and thank you, Shaynell. You could put your. Oh, that was a no, Shaynell. Wait, is it not clear? Wait.
That was an accident, sorry.
Oh, okay, no problem, no problem. Oh, thank you for your voice. That was just points for the voice too. Okay, so then here's my other question. Because you are going to work on this for a few, I will clear it up by the end of the class, but I also want to clear up these logistics. So let me ask you this. Would you guys raise your electronic hand if you would like to be in breakout rooms for this? Okay, that's a big no. All right, so I'm just gonna I'm taking that. Raise your hand if you would not like to be in breakout rooms for this. I just want to make sure there's okay, okay. Wow, I just learned something very deep. All right, fair enough. I know I will, it won't always be a vote, but it is this time. So all right. So I'm gonna shut up. You're gonna work on this for a few minutes. I'm gonna look at the Google, and then also while you're working, or especially if you get, and I'm gonna ask you. I'm ultimately gonna ask you to put something in the chat as either an answer or here's where I'm stuck, or I understand the question but I have no idea. Put something in the direct chat once you either get to an answer or you get to a stumbling block or whatever, just so I know. But also, please put in the direct chat. I think we all sort of put in the direct chat if we all confirmed like the date for our exam. Like I think I last time I saw you, I asked you to sort of go away and could, and you can do that now too if you. But I'd like to have a confirm. I think we had a suggested requested date, or I gave you two choices. If you could put in the direct chat like what we landed on, so I'll try to also confirm that, and that would be good. So I'm going to shut. Democracy said no. Right. Okay. All right. So I'm going to shut up. I want you to work on this, but any feedback you want to give me in the direct chat right now about this or what we said about the exam would be helpful. And I'm going to look and try to readjust your homework dates while we do.